Welcome! Today, we'll be tackling LeetCode problem number 1577, titled Number of Ways Where Square of Number is Equal to Product of Two Numbers. This problem is an excellent opportunity to practice working with arrays and mathematical relationships. Let's dive into the details and explore efficient ways to solve it. In this problem, we're given two integer arrays, nums1 and nums2, and our goal is to find the total number of triplets, I, j, k, that satisfy two specific conditions. First, we need to count the triplets where the square of an element from nums1 is equal to the product of two distinct elements from nums2. Specifically, for nums1, I, 2 to equal nums2, j, asterisk nums2, k, the indices j and k must be different. Similarly, we also need to count the triplets where the square of an element from nums2 is equal to the product of two distinct elements from nums1. This means that nums2, I, 2 must equal nums1, j, asterisk nums1, k, again ensuring that j and k are distinct. Finally, we sum the results from both conditions to get the total number of valid triplets. The output of this problem is a single integer, representing the total number of valid triplets that meet the criteria described. Let's look at an example to better understand. For nums1 equal to 7, 4, and nums2 equal to 5, 2, 8, 9, the output is 1. This is because there is only one triplet that satisfies the condition, where nums1, 0, 2, or 7, 2, equals the product of nums2, 1, and nums2, 2, which is 2 asterisk 8. This means the triplet, 0, 1, 2, is valid. In this example, no triplets satisfy the reverse condition where the square of an element in nums2 equals the product of two elements in nums1. Since there are no valid triplets for the reverse condition in this example, the total number of triplets remains 1. Now, let's look at another example to see a scenario where both conditions contribute to the final result. For nums1 equal to 1, 1, and nums2 equal to 1, 1, 1, the output is 9. Here's why. For each element in nums1, the square is 1, and there are 6 valid pairs, j, k, in nums2 where the product is also 1 because all elements in nums2 are 1. This gives us a total of 6 triplets. On the other hand, for each element in nums2, the square is also 1, and there are 3 valid pairs, j, k, in nums1 that satisfy the condition. This adds 3 more triplets. To summarize the calculations for this example, the 6 triplets from the first condition and the 3 triplets from the reverse condition give us a total of 9. Now, consider a final example where nums1 is 2, 2, 4, and nums2 is 1, 2, 3, 6. The output here is 4. First, for the condition where nums1, I, 2 equals the product of two elements from nums2, there is one valid triplet. Specifically, nums1, 2, 2, or 16, equals nums2, 1, asterisk nums2, 3, which is 2 asterisk 6. Next, for the reverse condition where nums2, I, 2 equals the product of two elements from nums1, there are 3 valid triplets. All 3 involve nums2, 3, 2, or 36, being equal to the product of 2 and 4 in various combinations. Adding up the results for this example, we have 1 triplet from the first condition and 3 triplets from the reverse condition, giving us a total of 4. To summarize the problem, we are tasked with finding all valid triplets for both conditions, ensuring that the indices j and k are distinct in each case. The constraints allow for array sizes of up to 100 elements, and the values in the arrays can go up to 10,000. It's important to consider edge cases, such as arrays with no valid triplets, arrays with all identical elements, or arrays that are too small to form any triplets. The solution needs to efficiently handle all these scenarios to compute the correct total. To solve this problem, we are tasked with finding the number of triplets where the square of a number from the first array equals the product of two numbers from the second array, with the condition that the indices of the second array are distinct. This requires careful consideration of all possible combinations of indices between the two arrays. The challenge here is to achieve a solution that is both correct and efficient, given the constraints. We need to evaluate different approaches to balance computational complexity while ensuring accuracy. One approach to solving this problem is the brute force method. The intuition behind this approach is straightforward. For each number in the first array, calculate its square and then compare it against the product of every possible pair of numbers in the second array, ensuring that the indices of the pair are distinct. This can be implemented using 3 nested loops, where the outer loop iterates over the first array and the inner 2 loops iterate over the pairs in the second array. However, the complexity of this approach is n1*n2, making it computationally expensive and impractical for larger inputs. To address this inefficiency, we can turn to an optimized approach using a hash map. Here, we pre-compute the frequency of all possible products from the second array and store them in a hash map. This allows us to quickly check how many pairs produce a specific product, eliminating redundant calculations. The same logic can then be applied in reverse to handle the symmetry in the problem, where the square of a number in the second array is compared to products from the first array. This reduces the overall complexity to n1*2 plus n2*2, which is a significant improvement. While the hash map approach is efficient, it comes with the trade-off of additional space usage for storing the frequency map. However, the time savings outweigh this cost, especially for larger inputs. Another approach we considered is the two-pointer method, which is often useful for finding pairs in sorted arrays. The idea here is to sort the arrays and then use 2 pointers to find pairs matching the target product. While this method is efficient in terms of time complexity, with sorting taking n log n, and pair searching taking n squared, it introduces complications. Sorting the arrays may disrupt the original index constraints of the problem, and additional effort is required to handle duplicates. These factors make the two-pointer approach less desirable for this specific problem. One key insight that simplifies the problem is recognizing that the frequency of products in one array can be reused to efficiently check multiple squares from the other array. This symmetry between the two arrays means we only need to implement the logic once and apply it in both directions. The hash map approach stands out as the optimal solution because it balances time and space complexity effectively. While it requires extra memory for the frequency map, the dramatic reduction in time complexity makes it the most practical choice. The brute force approach, while simple to understand, is computationally infeasible, and the two-pointer method introduces unnecessary complexity. By pre-computing product frequencies, we achieve a solution that is clean, efficient, and scalable, making it well-suited for competitive programming scenarios. In this problem, we are tasked with finding the number of triplets across two arrays, nums1 and nums2, that meet specific mathematical conditions. First, we check if the square of an element in nums1 equals the product of two distinct elements in nums2, ensuring the indices of those two elements are not the same. Similarly, we reverse the check, determining if the square of an element in nums2 equals the product of two elements in nums1, again ensuring distinct indices for the product pair. This requires us to carefully analyze the relationships between the elements in both arrays and systematically count the valid combinations that satisfy these conditions. To solve the problem, we can break the algorithm into several steps. First, we need to understand the quadratic relationship. For nums1, i2 to equal the product of two elements in nums2, we fix nums1, calculate its square, and search for pairs in nums2 that multiply to this value. Similarly, for nums2, i2, we fix nums2, compute its square, and search for pairs in nums1. Next, to make these searches efficient, we use a hash map. This hash map will store the product of two numbers as the key and the count of pairs producing that product as the value. To prepare for this, we pre-compute the pair products for both arrays. By iterating through each array, we calculate all possible products of pairs where the indices are distinct and store these in the hash map. This pre-computation step allows for quick lookups later when verifying the conditions for valid triplets. Once the pair products are pre-computed, the next step is to iterate through the elements of nums1 and nums2. For each number in nums1, we compute its square and use the pre-computed hash map for nums2 to find all pairs whose product matches this square. The count of such pairs is added to our result. We then apply the same logic in reverse, iterating through nums2, computing the square of each number, and checking the pre-computed hash map for nums1. Additionally, we need to handle edge cases. Duplicate values in the arrays require careful attention, as they increase the pair counts, and we must ensure the indices of the pairs are distinct. Special handling is also required for zeros, as the product of any number with 0 is always 0, which could lead to invalid triplets if not managed correctly. There are several key insights that make this algorithm efficient. First, pre-computing the pair counts eliminates the need to repeatedly calculate products for every query, significantly reducing redundant computations. Second, the use of a hash map enables fast lookups, achieving an average time complexity of 0.1 per query. Third, the problem structure is symmetrical, meaning the same logic applies for both nums1 and nums2, simplifying the implementation. Finally, it's critical to ensure we avoid double counting by explicitly enforcing the condition that the indices of the pair, j and k, must be distinct. The main data structures we rely on are the hash map, which stores the counts of pair products, and the input arrays, which we use to iterate over elements and compute their squares. Analyzing the complexity of this approach, the most computationally expensive step is the pre-computation of pair products for each array. This involves iterating through all pairs of indices, resulting in a time complexity of n squared, for nums1 and m squared, for nums2, where n and m are the sizes of the arrays. Querying the hash map for each square involves iterating through the elements of nums1 and nums2, which is m and n, respectively. Combining these steps, the overall time complexity is n squared plus m squared. The space complexity is also n squared plus m squared, as we need to store the pre-computed products in the hash maps. This balance between pre-computation and efficient querying ensures the algorithm is optimized for this problem. To better understand the algorithm, let's walk through an example with nums1 equals 3, 1, 4, and nums2 equals 1, 2, 6. First, we pre-compute the pair products for both arrays. For nums1, the products are 3, 12, and 4, which we store in a hash map as 3, 1, 12, 1, 4, 1. For nums2, the products are 2, 6, and 12, stored as 2, 1, 6, 1, 12, 1. Next, we iterate through nums1. For nums1, 0 equals 3, we compute its square, 9, and check the nums2 hash map for pairs with a product of 9. Since no such pairs exist, there are no valid triplets for this case. We continue this process for the other elements in nums1 and nums2, summing the counts of valid triplets. Now, iterating through nums2, we start with nums2, 0 equals 1. Its square is 1, but checking the nums1 hash map reveals no pairs with a product of 1, so no valid triplets are found for this case. This process is repeated for all elements in nums2, ensuring we account for every valid triplet. By leveraging the pre-computed hash maps and iterating through both arrays, this approach strikes a balance between correctness and efficiency. It avoids redundant calculations while ensuring all valid triplets are counted accurately, meeting the problem's requirements effectively. Here, we define the number triplets function inside the solution class. This function takes two lists, nums1 and nums2, and aims to count the number of valid triplets where the square of one number equals the product of two others. Inside the function, we have a helper method called count_triplets that handles the core logic. It starts by initializing a counter to keep track of the total triplets and a counter object called product_counts to store the frequency of numbers in the second array, b. This frequency map will allow us to quickly check if a number exists when needed. Next, for each number x in the first array, a, we calculate its square, denoted as x_squared. The goal is to find pairs of numbers in B whose product equals x_squared. To do this, we iterate over all elements in B and check if x_squared is divisible by the current number. If it is, we calculate the complementary value, called pair_value, which is x_squared divided by the current number. We then check if this pair_value exists in the frequency map. If the pair_value matches the current number, we subtract 1 from its frequency to avoid double counting, since the same number is being used twice. Otherwise, we simply add the count of pair_value to our triplet counter. Finally, since pairs, j, k, are symmetric, we divide the total count by 2 to ensure we don't overcount. The final step in the implementation is to return the total number of triplets. We achieve this by calling the count_triplets function twice, once with nums1 as the first array and nums2 as the second, and then with the roles reversed. This ensures we account for all valid triplets, regardless of the order of the two input arrays. By summing the results of these two calls, we obtain the total number of triplets where the square of a number in one array equals the product of two numbers in the other. This approach ensures we cover all possible combinations efficiently. Here, we begin with the Java implementation of the solution. The main method, number triplets, takes two integer arrays, nums1 and nums2, as input and returns the total number of valid triplets. To achieve this, we call a helper method, countTriplets, twice, once with nums1 as the first array and nums2 as the second, and then vice versa. This ensures we cover all possible combinations where the square of an element in one array equals the product of two elements in the other. In the countTriplets method, we start by creating a hash map called productCounts to store the frequency of the squares of elements in array B. We iterate through each number in B, compute its square, and update the map with its occurrence count. Next, for each element x in array A, we calculate its square, x squared, and then iterate through each number in B again. If x squared is divisible by the current number, we calculate the corresponding pair value by dividing x squared by that number. To prevent potential overflow, we skip the iteration if the pair value exceeds the integer.max_value. Finally, if the pair value is equal to the current number, we decrement the count by 1 to avoid overcounting self-pairing cases. However, if the pair value is different from the current number, we simply add its frequency from the productCounts map to the count. This accounts for all valid pairings for the given x in array A. After iterating through all elements in both arrays, we return the total count divided by 2. This adjustment is necessary because symmetric pairs, such as x, y, and y, x, would have been counted twice during the process. The implementation ensures that we efficiently calculate the number of valid triplets while avoiding redundant computations and potential overflow issues. The combination of clear logic and proper handling of edge cases ensures that this solution is both robust and optimal. In this example, we start by defining the count_triplets function. This function takes two arrays, A and B, and counts the number of triplets where the square of a number from array A equals the product of two numbers from array B. To solve the problem, we will call this function twice, once with nums1 as A and nums2 as B, and then again with the roles reversed. For the first call, we initialize A as 3, 1, 4, 1, 5, and B as 2, 7, 1, 8, 2. We also create an empty dictionary, product_counts, to store the frequency of numbers in B, and set count to 0. The first task is to populate product_counts with the occurrences of each number in B. After processing, product_counts becomes 2, 2, 7, 1, 1, 1, 8, 1. This frequency map will be crucial for quickly checking how many times a potential product appears in B during the next step. Next, we iterate through each number x in A to find triplets. For each x, we calculate x_squared, the square of x, and then check all possible pairs in B to see if their product equals x_squared. Starting with x equals 3, we calculate x_squared equals 9 and test all numbers in B. None of the pairs divide 9 evenly, so we skip all of them. For x equals 1, x_squared equals 1, and we again check all pairs in B. Here, we find that 1 divides 1 evenly, but the pair value 1 appears only once in product_counts, which means there are no valid combinations. Continuing this process for x equals 4, x equals 1, and x equals 5, we similarly find no valid pairs. By the end of this step, the result of count_triplets, nums1, nums2, is still 0, as no triplets satisfy the condition. Now, we make the second call to count_triplets, this time with nums2 as A and nums1 as B. We repeat the same process, starting with initializing product_counts for nums1 and iterating through each number in nums2. However, like the first call, no valid triplets are found. This means the intermediate result of count_triplets, nums2, nums1, is also 0. Adding the results of both calls, the total count for this example is 0 plus 0 equals 0. Moving to the next example, we now consider nums1 equals 7, 4, and nums2 equals 5, 2, 8, 9. For the first call, product_counts is computed for nums2, resulting in 5, 1, 2, 1, 8, 1, 9, 1. This frequency map will again help us efficiently look up potential products. Next, we iterate through each number in nums1. For x equals 7, we calculate x_squared equals 49 and check all pairs in nums2. However, none of the pairs in nums2 multiply to 49. Similarly, for x equals 4, x_squared equals 16, and no valid pairs are found in nums2. As a result, the first call of count_triplets, nums1, nums2, gives 0 valid triplets. For the second call, where nums2 becomes A and nums1 becomes B, the process is repeated, but again no valid triplets are found. Adding both results, the total count remains 0 plus 0 equals 0 for this example. Now we proceed to the third example, where nums1 equals 1, 2, 3, and nums2 equals 1, 2, 6. As before, the first step is to compute product_counts for nums2, which gives 1, 1, 2, 1, 6, 1. In this final example, we iterate through each number in nums1. For x equals 1, we calculate x_squared equals 1 and check all pairs in nums2. While 1 divides 1 evenly, the pair value appears only once in product_counts, so no valid triplets can be formed. For x equals 2, x_squared equals 4, and no pairs in nums2 multiply to 4. Similarly, for x equals 3, x_squared equals 9, and no valid pairs are found. After processing all numbers in nums1, the first call results in 0 triplets. Repeating the process with nums2 as A and nums1 as B, no valid triplets are found here either. The total count for this example is again 0 plus 0 equals 0. This completes the walkthrough, showing that for the given examples, no triplets satisfy the condition of the problem. To analyze the time complexity of our solution, we start by breaking it down step by step. First, the function count_triplets is called twice, once with nums1 as A and nums2 as B, and then with the roles reversed. If we let n represent the size of nums1 and m represent the size of nums2, this means we are performing two major computations. Next, within each call, we use a counter to calculate the frequency of elements in the array B. Since this operation iterates over all m elements in B, it takes m time. Then, we move on to the outer loop, where we iterate over each element in the array A. For each of these n elements, we compute its square, x_squared, which is a straightforward O(1) operation. These steps set up the framework for the nested iteration, which we will examine next. Now, let's focus on the inner loop. For each element x in the array A, we iterate through all m elements in the array B. For every pair x number, we check if x_squared is divisible by number and, if so, compute the corresponding pair underscore value. This results in m iterations for each of the n elements in A, giving us a total of n*m iterations for the nested loop. After that, we use the counter to check if pair underscore value exists in the frequency table, which is an O(1) operation. Any updates to the count variable are also O(1). Since the operations within the nested loop dominate the overall computation, the time complexity of a single count_triplets call is n*m. Since we call count_triplets twice, the total time complexity becomes n*m plus m*n, which simplifies to n*m. Let's now analyze the space complexity of the solution. The primary contributor to space usage is the counter, which stores the frequency of unique elements in the array B. In the worst case, if all elements in B are unique, the counter will require m space. Besides this, the algorithm uses only a few additional variables, such as count, x_squared, pair underscore value, and the loop iterators, all of which require constant space, or O(1). Importantly, we only maintain one counter at a time, regardless of the two calls to count_triplets. Therefore, the overall space complexity is determined by the larger of the two arrays, leading to O max n*m. When comparing the optimized solution to a brute force approach, the improvements become clear. A naive method would involve iterating through every pair of elements in B for each element in A. Specifically, for each x in A, we would check all possible pairs, j, k, in B to see if x_squared equals the product of B, j, and B, k. This leads to a time complexity of n*m squared, as the inner loop would have m squared iterations. In contrast, the optimized approach uses a counter to reduce the inner loop complexity from m squared to m, resulting in a significantly improved time complexity of n*m. For best, average, and worst-case scenarios, the optimized solution maintains the same n*m complexity, as it always processes the elements of both arrays fully unless one of the arrays is empty, in which case the function exits early with O(1) complexity. Finally, let's verify the big O complexity mathematically. The outer loop iterates n times, and for each iteration, the inner loop iterates m times. This gives us a total of n*m iterations, which corresponds to O n*m. The operations involving the counter, such as insertion and lookup, are each O1, and no additional nested loops are present in the algorithm. This confirms that the time complexity of the solution is indeed O n*m, as we derived earlier. The use of efficient data structures like counter allows us to achieve this complexity without increasing space requirements beyond O max n*m. When solving this problem, there are a few common mistakes that can trip you up. First, it's essential to enforce the condition that the indices j and k in nums2 must be distinct. If this condition is ignored, you might accidentally count invalid combinations where j equals k, leading to incorrect results. To fix this, you can use nested loops or carefully designed data structures to ensure j is not equal to k. Next, a naive approach that checks all combinations of I, j, and k using triple nested loops would have a time complexity of O n cubed, which is inefficient and likely to time out for larger inputs. Instead, hash maps can be used to pre-compute products or frequencies, significantly reducing the complexity. Another mistake is misinterpreting the problem's constraints, such as assuming nums1 and nums2 are of equal length when the problem doesn't guarantee this. Always read the constraints carefully, and make sure to handle cases where the arrays have different sizes. Finally, if nums2 contains duplicates, you need to account for the number of valid pairs, j, k, for a given product. Failing to do so might lead to undercounting. Using combination counting, like calculating n choose 2, can help you handle duplicates properly and ensure all valid pairs are counted. Another potential pitfall involves overflow issues when dealing with large values in nums1 or nums2. The square of an element in nums1 or the product of two elements in nums2 can exceed the limits of standard integer types in some languages. To address this, you can use a language like Python, which supports arbitrary precision integers, or implement overflow handling techniques in languages like Java or C++. From an interview perspective, it's crucial to focus on optimizing your solution using hash maps, as interviewers often assess your ability to reduce complexity in pair counting problems. Demonstrating how you can refine a brute force approach into a more efficient one highlights strong problem-solving skills. Additionally, discussing edge cases upfront, such as empty arrays, arrays with duplicates, or arrays containing zeros, shows your attention to detail. Communicating trade-offs is also important. For instance, you might explain the decision between using extra space for hash maps to optimize time complexity versus sticking to a brute force approach that uses less space but is slower. Lastly, for languages with fixed integer sizes, practicing modular arithmetic to handle potential overflow issues can be a helpful skill. This problem is conceptually related to several other problems on LeetCode, which are worth exploring to deepen your understanding. For example, LeetCode 15, known as 3-sum, also involves finding triplets but focuses on finding combinations that sum to 0. Similarly, LeetCode 18, or 4-sum, extends the concept to quadruplets, where you search for sets of 4 numbers that satisfy a sum condition. A foundational problem to revisit is LeetCode 1, 2-sum, which introduces the hash map-based pair counting technique that is key to optimizing solutions for problems like this one. Another closely related problem is LeetCode 1726, tuple with same product, which involves counting tuples that satisfy a specific product condition. By studying these related problems, you can gain valuable insights into pair and triplet enumeration techniques and improve your ability to identify patterns and apply similar optimization strategies across different scenarios. To solve this problem, there are several approaches you can consider, each with its own trade-offs. The brute force method, which involves triple nested loops, is conceptually straightforward but highly inefficient with a time complexity of O n cubed. While this approach is suitable for small input sizes, it's impractical for larger arrays. On the other hand, using a hash map for frequency counting is a more optimized approach. Here, you can store the frequency of products in nums2 and then check if the product exists in the hash map for each square in nums1. This method reduces the time complexity to O n squared, but requires additional space to store the hash map. Another alternative is the two-pointer technique, which can be applied when nums2 is sorted. By using 2 pointers, you can efficiently find valid pairs, j, k, that satisfy the product condition for a given square in nums1. However, this approach comes with the overhead of sorting nums2, which adds O and log n to the overall complexity. Each method has its strengths and weaknesses, so the choice of approach depends on the problem constraints and the trade-offs you're willing to make between time and space efficiency. Thank you for joining me in solving problem number 1577. We summarized the key approaches, discussed algorithmic efficiency, and highlighted important takeaways. Don't forget to practice similar problems to strengthen your understanding. I'll see you in the next session. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!